Good afternoon, everyone. Thank you for joining us in this webinar on Peak Force TUNA training. Today, we're glad to have Dr. Christian Freck, our customer support engineer based in Germany. Christian has obtained his PhD at University of Dresden with a research topic in situ electrochemical scanning probe microscopy of the deposition of conducting polymers. Until today, Christian has 25 years of experience in scanning probe microscopy. For today's webinar, we'll focus on topics such as tunneling AFM TUNA, Peak Force TUNA, torsion TUNA, data channels, troubleshooting, and probe selection. At the end, we'll have 15 minutes Q&A session, and we'll also send you by email the presentation slides as well as the webinar recording after the webinar. Okay, let me pass the wheel to Christian. Please go ahead.
Good afternoon, everybody. So this is Christian Freck from Bruker, Germany. As already mentioned, this presentation is about TUNA, tunneling AFM, and Peak Force TUNA. Most of the data and slides were created by my colleague Jürgen Huhr from Santa Barbara, and I added some slides to that. So what are the contents today? So again, something about the basic measurement principle of the tunneling AFM, the hardware and the modes for measuring current with an AFM, and excuse me, and then about the parameters for the open loop and closed loop tuner measurements. I will also cover a bit of IV spectroscopy, so in the ramp mode and in the point and shoot mode. Something more about the Peak Force TUNA hardware and its parameters. A brief introduction to torsion TUNA to complete this set of current measurements. Then something about the sample preparation, troubleshooting, and the probes we can provide for TUNA measurements. So starting with conductive AFM TUNA or Peak Force TUNA, all of them are using the same technique. You have a conductive tip which is in contact with the surface. So like in contact mode, Peak Force TUNA mode, or in the torsion mode. And you have a bias voltage between the probe and the sample. And the electrical current going through the tip is then measured and amplified and sent to our controller. And you can get an image of your topography and your current data simultaneously, or also in the case of torsion TUNA, for instance, in interleaf mode. The ranges we are talking about for the current are, let me start at the top. For the application modules, for the Peak Force TUNA goes from 100 femtoamperes up to 1 microampere. The lateral resolution is about 10 nanometers, is more or less limited by the tip itself. The second module nowadays available is the TUNA module, which is not capable of Peak Force TUNA, but for the measurement in contact mode, the standard TUNA measurements goes from 80 femtoamperes to 1 microampere. Again, the tip is the limit there, with 10 nanometer maximum lateral resolution. The scanning spreading resistance microscopy is a different module capable of also measuring the current in the range from 10 picoamperes up to 0.1 microampere, so it's a much smaller range, but can be used for different purposes, like for semiconductors. The conductive AFM, which is let's say the oldest form of measuring tunneling current with an AFM, the CAFM has a range from 1 picoampere to 1 microampere. Again, lateral resolution is limited by the tip and is about 10 nanometers. The hardware modules, so like the conductive AFM and the TUNA 2 module, they have a trim pots to adjust the offset and the gain to have the measurement set up correctly when you calibrate the system. The TUNA 2 module doesn't have a trim pot any longer easily available, so it's nothing you should worry about. It's preset and pre-calibrated and it's calibrating itself more or less. The Peak Force Tuner module has a mechanical switch, which is then the main difference, where you can see where you can switch between high and low gain, which allows you then up to 6 different sensitivity ranges. And the TUNA 2 module, in addition, has also a ground pinhole where you basically contact, in the case of measuring in tuner mode, to reduce the noise of the system. With all the possible sets or modules comes also a test resistor, which has a range from about 10 giga ohm to 1 mega ohm. And for testing, you should connect the test resistor to the module. You would have to mount a conductive tip to get a laser sum for the icon system. That's not necessary for the multimode. Then you would force engage and select the ramp mode and display the tuner current while sweeping a test bias. But I'm coming to that later again on an extra table concerning the troubleshooting. And then you would basically look for your IV curve there. For the hardware itself, you have an electrical probe holder, which can be used for tuner, SSRM, or extended torsion. That's called the extended holder, which can be used again for torsion tuner, standard tuner, or SSRM. So spreading resistance measurements as well. Here you can see on this image that there's a grounding wire which is connected. Again, this would go into the ground from the module, but only for tuner, not for Peak Force Tuner. It's not used any longer. It's not needed. This is the standard holder, or this is the holder for the measurements for the icon system. I have later a picture of the multimode holder as well. One of the things you can, for the icon, what was also of importance here is that this can be used if you go for laser alignment on the icon system. And the software is asking you if you want to go to the alignment station. This has the same height dimensions as the standard holder, so you can use also the alignment station for the tuner holder to align your laser on the cantilever. Again, so this holder can be used for conductive AFM contact tuner or Peak Force Tuner. And when you're using it for contact tuner measurements with the TUNA 2 module, then the ground pin connects to the ground on the module. Again, not for Peak Force Tuner. Here are some images, and you have to see the differences between the open loop tuner on top and the closed loop tuner underneath. So basically, open loop tuner keeps the bias between the tip and the probe constant and is measuring then the current as an answer. So you will see different intensities of your current depending on your voltage and how good the surface is conductive. On the closed loop tuner, the feedback tries to keep the current constant and therefore changes the bias locally during the measurement. How to turn this on and off? So in our software, you find then under the tuner reading in the real-time mode, the feedback mode is either enabled or disabled. If you enable it and you're working in closed loop tuner, then the closed loop tuner can limit the current to a given value to avoid damage of the sample or the tip if your voltages would be too high. These are the ramp parameters. If you go to the ramp mode for IV spectroscopy, you would select for at first the ramp output is not as done at the Z height or the height sensor, but in this case the sample bias. You can set up here in the your begin and end potential, how fast you would like to run it, and then you would basically can select if you want to go with a single ramp or a continuous ramp, if you want to stop the ramping or want to have a continuous approach, or for instance, if you want to have more than one IV curve, you can go to the auto ramp and have it then automatically set up a small matrix where it would run the IV curves. Also, in addition to that, you can also apply different feedbacks here, and here is another option, which is then the point and shoot, where you can use the AFM image, collect the AFM image, and then you can select the areas where you would like to measure the currents, and then you would get the tuner current as an answer to your local measurements. Here you can see an overview of the point and shoot parameters. So basically, at first you should obtain an image, and then you could set up the points of interest either by using, like here, a box where you can just have a row of data points, or you can simply select them individually. So it depends on you if you just point them or if you convert a box into a grid, into a raster where it would measure each and every point after each other. So for the point and shoot can capture ramp curves on multiple desired locations, again with various settings here. In the save data, these force curves are then linked to the AFM images that you can basically go locally to the area of interest, click on that, and then you instantly see the force, or in this case, IV curve, if you select the correct channel for it. All the settings you can, for the point and shoot measurements, where you do the ramping, can be set up in the ramp, and then you switch back to point and shoot, and then you can adjust there your settings and then your locations, and you start the collection of the data. Something about the Peak Force TUNA module here. Why do we need a new module after we had the TUNA 2 module? There, basically, it has a higher bandwidth and a higher gain, which allows you now much better signal to noise ratio. Therefore, we had to create, or we created a new module where actually also the peak force frequency, usually 2 kilohertz, is nicely far away from any resonance frequency of the cantilever. So therefore, you have less noise in the electronics actually. What can we measure in Peak Force TUNA? So it's using the peak force technique, where we have a forced oscillation at, depending, let's say 2 kilohertz or down to 0.125 kilohertz. So your tip is moved not at a resonance frequency, but much, much lower. And you would press onto the surface till you are at certain stable conditions, that you have a good contact with the surface, but without being too aggressive. So it's much less aggressive than contact mode, and also much less aggressive than tapping mode. If you are in tapping mode, it might be sometimes the first approach might also be too aggressive. It might damage your tip, and this is one of the disadvantages of contact mode tuner. You have a good contact there, but however, you have your metal coated tip, and this metal might wear off due because you have lateral forces when you move your tip over the surface, always in contact. Therefore, Peak Force TUNA is much more gentle to the coating of metallic coating of the tuner tip, and it's giving you better and more consistent results. So what we can measure here, so one is called the peak current, which is at the position C, which means where the force is maximized before the system is retracting the tip from the surface. So that's the strongest point of contact. So this is the so-called peak current. Then you have the contact current, which basically goes from the snap into contact, which is here point B, and goes then back to point D, where the tip snaps off from the surface, and the current is measured the whole time when there's a tip is in surface with in contact with the surface. And thirdly, we have the tuner current to be displayed, which is then basically going through the whole cycle from A to E. So basically, even when the tip is not in contact with the surface, like in induction could take place, and you can measure there the tuner current, so which is more or less the integral over all currents. So the data here, you can see here images from a height sensor, and then simultaneously you can select in all peak force modes up to 8 channels. And you can have here the tuner current, the peak current, and the contact current in the same image, and you get a map of your current distributions there, which allows you then to see where you have areas of higher or less conductivity. The key parameters for the Peak Force Tuner actually are more or less as usual the peak force set point, so the force applied from the tip towards the surface, and also the amplitude. Basically, if you want to have a more consistent measurement, it is good to increase the contact time. In this case, you can increase the set point and or reduce the peak force tapping amplitude, which means then that your tip stays longer on the surface when your amplitude is smaller. So the good thing about the Peak Force Tuner, and this is a big advantage again over the contact tuner measurements or also conductive AFM measurements, it enables reliable nanoelectrical imaging on soft and delicate samples like loosely bound nanostructures or conductive polymers. It also improves the imaging resolution and the tip lifetime while making conductive AFM measurements easier, and it enhances material assignments on the nanoscale, so you get your nanomechanical properties and your nanoelectrical properties at the same time. Again, let me just rephrase: if you are using contact AFM methods like the standard tuner or standard conductive AFM measurements, you always have the problem that your metallic or conductive tip might wear off fast, and therefore your images might not be consistent, or even one full frame is hard to find. So if your set point is too high or has to be high to stay on the surface, it might happen that your tip coating might wear off while you're scanning over the surface, and therefore Peak Force Tuner is the much better method of choice. So a brief introduction to the torsional mode, or TR tuner, where we use the torsion mode. So your tip is then, the cantilever is twisting in torsional mode at resonance frequencies in the range of 1 megahertz instead of the usual, let's say, 150 or 80 kilohertz for this kind of cantilevers. And by this twisting motion, and you would go down touch the surface, and your contact time is there also longer, and your tip is going from, your pyramid is more or less going from left to right and touching the surface also with a broader or wider area, bigger area, sorry, and therefore you have more contact area, and therefore you can obtain a better current flow there. The torsion mode can be combined with a tuner, but again, it is not easy to operate the torsion motor, but I just wanted to mention it here because it can give you better results on, for instance, small steps on surfaces when they are conductive at the edges. Then you can get a much better contrast there. So here's a comparison between these AFM-based measurements, this between Peak Force Tuner, Contact Tuner, and Torsion Tuner. So all of them, of course, are capable of showing you a map of the conductivity of your surface. The forces you can see here have lots of differences here. So you have the minimum force can be lower than 100 piconewtons for the Peak Force Tuner, so almost very, very small forces. Contact Tuner already is at the range of 10 nanonewtons. This doesn't apply to the Torsion Tuner here. Peak Force Tuner is the only technique where you can have simultaneously also the quantitative nanomechanical mapping. As for ease of use, Peak Force Tuner and Contact Tuner are the easiest methods. Again, contact, abbreviation of your metallic or conductive layer. Peak Force Tuner less aggressive to the tip coating. Torsion Tuner, again, is not easy to operate, so it's hard to get the proper conditions and to work properly there. Something about the sample preparation. Usually, again, it is needed to have your probe or your surface of interest needs to be on a metallic plate, which is then made conductive by either soldering or by conductive glue or silver paint, so that your current is flowing through the metallic disc and through your sample to the surface. And in the case if you have very conductive samples like a gold layer or even HOPG already, it is better to make this contact via a resistor in between in the range of 10 to 100 mega ohm to limit the current flow. Otherwise, the tuner is too sensitive and you show mostly only noise. So yes, are some hints for the troubleshooting for a no good or a bad tuner signal. So one is, again, like in the measurements I mentioned before, you increase in Peak Force Tuner the set point on and or lower the peak force amplitude to have a longer contact time and therefore more current flow. The other thing is to start out with would take another probe. Maybe the probe is already worn off, that there's no metallic coating which could sense the current. One other thing is to check also the conductivity from the metal plate we had before to the top of the sample. So you would basically measure from the bottom of the metallic plate to the top here with a ohm meter and would measure the resistivity there. What I had also in at various situations is that basically to check if your applied bias is really applied between your sample and the ground. So technically from the multimode base, in the case of the multimode, to the sample, or for instance from the icon dovetail where you put your scanner in to the sample on the chuck, the applied bias should be the one you typed in the sample bias for your measurements. And if this is a huge difference, then you have to check again if your sample is connected correctly. If this is not the case, please check your sample. And then again, we have also the possibility to check the module with your test resistor for all ranges and sensitivities. I'm coming to the details on the next page. And also to check the conductivity from the probe substrate to the holder, to the connector at the end of the cable, which means basically, I'm starting with the right-hand side here with the extended torsion tuner holder. Basically, you would measure here from the substrate, where at the very end is the cantilever. You don't have to measure from the cantilever, but the substrate bottom side is also coated with the same metal or conductive surface. And then to the end of the cable in between, there should be the resistance should be 0. If you don't want to measure on the tip, you can also put a small sharp tweezer in here and just hold it down with a clamp, and then you would measure the same from the tweezer to the end of the cable. Again, the resistance should be 0. And here's the holder for the multi-mode on the left-hand side. And you would measure here also from the tip holder to the back side of the holder, where this usually is the cable connector. Sometimes, and this is for the multi-mode only, there's coming with the multi-mode also a small metal shield, which basically would shield out any stray field. You would make your multi-mode head Faradaic cage. And basically, you can, with this metallic sheet, you can basically shut out all electrical fields completely, so that nothing is interfering from outside your optical head from the multi-mode. And just remember, so the bias you can apply usually for the tuner is maximum plus minus 10 volts. However, 10 volts can already, with a high current flowing, can already damage your platinum coating on the most of the tips. So therefore, be careful with that. Usually, I would start out at, let's say, 500 millivolts, and looking for my tuner response also in Peak Force TUNA, and I would increase it slowly in steps of 500 millivolts further. And if you have, for instance, the KPFM sample with a tuner together, then it should start to work, to show you a current flowing in the range of 3 to 4 volts. If this is happening later, usually you have some insulating or insulating layer in between, some bad connection somewhere. Please check that before you increase your voltage higher, at least on a standard sample like the KPFM standard sample. Here are the settings for the testing of the module with the test resistor. Again, you should align a laser on the cantilever, and you need to connect the module to the controller in the case of the multimode with the applications module cable, or to the icon stage. You connect the test resistor, then use the force engage, either selecting force engage from the microscope menu, or you press Ctrl-Alt-F. You open after that you open the ramp mode, and then you see down here the parameters for each setting for the sensitivities for the Peak Force TUNA module, from 100 nanoamperes down to 20 picoamperes. And for each and every one of these, you would run with these settings of your test resistor ramps in the ranges between 10 volts, or for instance here for 0.5 volts, and look for the tuner current. Usually you should get a straight line like on any resistor where you apply such a ramp in DC. So be aware of, if this is there, then your module is working, so the cause of error why your system is not giving good results is somewhere else. And by the way, please, in this case, use not sample bias, but test bias to ramp. The probes to use, basically, there's a huge list I have here from our probes site, Bruker AFMprobes.com, where you can look for tuner or PF tuner probes. The most common ones are the SCM PITs. The next one, so these are platinum iridium coated silicon probes. For Peak Force TUNA, they are usually fine. If you have would work rather in contact mode tuner, like standard tuner. We have diamond doped probes here as well. which are then using a diamond-like carbon film as a coating, which allow you then better mechanical stability with the slightly less conductivity. Then we have this AD. This is also diamond tips aspect, diamonds, so very sharp diamond tips. Again, SP2, SP3 carbon inside, which would allow you to measure the conductivity. They're pretty sharp. And the other ones down here are full metal tips, so like here a solid wire of platinum in this case at various spring constants as well. So these are made completely out of platinum, so there would not be a change for standard tuner measurements in contact mode. So your metal will always be conductive because it's always there. The only thing is you might have see changes in the lateral resolution over time if you wear off the tip, but it's still conductive. And further down here, you have, again, the new version, the version 2 of the PITs, just slightly different substrate, but similar properties. And the new tip here is SCM-PT-Si, which is platinum silicate, which is pretty new, and this is a new one, again, which should show better mechanical stability in standard tuner measurements and still provide a very good conductivity. Now a final word about the Bruker training option. So we are offering, as you see right now, webinars on specific topics, and I hope you enjoy the webinars. But we also offer training courses at the Bruker offices where users can meet, improve their knowledge, use the Bruker systems with the support of the experienced engineers on site, and discuss their specific topics or problems. And I just recently gave a couple of trainings, and I think everybody is benefiting from that. So the attendees, because they can interact with others and find similarities and help each other, and also they get more information and more hints while being on site. Usually these trainings are 2 or 3 days. And for 2018, we are thinking about a modular setup so that you can choose it's either 1, 2, or 3 days. It's right now in the planning state, but I think this is how we are going to do it next year. About the cost, so one seat is free of charge for customers with a warranty system, or with an extended warranty system, or with a platinum service contract. For academic customers, there will be a discount. And the fee will be announced with the training dates, which should then be available end of this year. That's it from my side, and now I'm open for questions, and thank you for your attention. Hello? Jan? Are you there? I don't hear Jan. Okay.
Here.
Good.
Yes, let's have our first question. It's from Chen Long. We have Peak Force TUNA module. Can we do SSRM mode? And this is the first question.
No, for this you need no. Yeah, no. You need to change the. You have to have a different for SSRM. You need to have a different module because it uses, strictly speaking, is not amplifying the current, but the resistance. Therefore, it's recalculating the current from that. But now you have to use the SSRM module with it.
Okay, and the second question is, when I set tip and sample bias as 0, but I still can find very low background current, is there a way to get rid of the background current?
That's a good question. I have to think about that a bit. I think there might be a slight bias on your system, so maybe you can just try to see what happens if you minimize one direction, change your sample bias slightly a bit more to the positive or to the negative, and see if the current gets less. This might be a problem, or you might have some induction coming to the system that you have to shield off your sample better. Again, this might be easy on the multi-mode where you have this metallic shield coming with a module. For the icon, I think there's a procedure mentioned in the online help.
Okay, thank you, Christian. And another question from Abdelila. Is this also available for the Resolve, because the Resolve does have a current amplifier already for CAFM?
I have to check for that. I'm not positive because I'm not an expert on the Resolve. I know, again, so that we can do their tuner measurements, and I'm pretty sure it will be also Peak Force Tuner, but I think right now it's a special and I have to ask, so please, if it wouldn't be too much, send me an email and I will follow up on that.
Okay, and we have another question from Maximilian. Regarding probes for Peak Force TUNA mode, there are also Peak Force TUNA. What is the main difference compared to SAM PIT probes, and for which samples should it be used?
Can you repeat the last part, please? What's the main difference between?
The main difference compared to SCM PIT probes.
Compared to what? Sorry, I'm just a bit lost here.
I think so Peak Force TUNA probes.
Oh.
So what's the,
Okay. Now I see. Yes, so the Peak Force TUNA probes are triangular, so they can be used. That's the idea behind them, is they can be much better used for softer material. So again, for delicate material like conducting polymers or some slightly coated nano wires, which are maybe out of soft material, the Peak Force TUNA probes have a much smaller spring constant and therefore are better to be used on softer material. So the SCM PITs are usually more used for semiconductors or metals and harder material.
Okay, so that's good. And another follow-up question from Chunlong. When we measure the IV curve, start from negative 5V to 5V, from negative 5V to 0, we can get negative current, but from 0 to 5V, the current away is 0. So is that the question?
So basically, he says that his IV curve is so is my question back is this what kind of module is it? Is it a Peak Force TUNA, or is it a standard TUNA or CAFM module? Because on the old modules might be that you have simply an offset in there, or that there's a problem.
Force TUNA.
It's Peak Force TUNA, okay.
And
is this the same? Would be then my next question in this case. Is this the same also for the test resistor, or is it only on the sample?
The point and shot.
It's in point and shoot. Okay. But this means it's only on the sample. So if the test resistor is fine, I'm just trying to understand. So maybe there's the system is then not conducting, but basically blocking, insulating. So like a semiconductor behavior there's at some point. That's the only thing I can think of, because I do not know nothing about the sample or the setup. But so if the test resistor is fine in the range, then the tuner module is fine, or the Peak Force TUNA module is fine, and then It can only be an effect of your sample, which is then basically getting insulating.
Does that answer to your question, Chenlong? If not, maybe you can contact the question in person later. And we have another question from Belen. All modes are with continuous contact by dragging the tip over the sample, or does tapping mode exist?
Again, so Peak Force is a Peak Force tapping method where we have an oscillation, not in tapping as in resonance, but tapping at 2 kilohertz or a bit less. So there we have we are not dragging the tip over the surface. So Peak Force TUNA is not dragging the tip over the surface as the CAFM or standard TUNA measurements.
So is there any other follow-up questions? Okay, that's good. So I think we have no more questions. Thanks for everyone to participate in this webinar. And just before you go, we're currently constantly trying to improve our webinar quality. So if you don't mind, could you just take 1 minute to answer our 4 little questions? So the first one is, have you already used Peak Force TUNA in your work? Okay, so we've got 75% of among us who have already used that. And we'll pass on to the next question. So what would best describe your situation between among learning, searching, investing, and purchasing? Okay, the third question, do you find the presentation related to your research? Okay, great. Last question, would you like to participate in our other webinars in the future? Okay, great. Thank you guys, and thank you again for your support. And we will see you in our next webinar. Have a good day.
Thanks, guys.
Bye.
Bye.